So here are some examples of things that we can do. We've discussed a couple of them already. Um, Within the raster data model, distances from roads, the density of characteristics in space. If we generate a couple different types of surfaces, we can say how long does it take us to get from place to place. The least cost path there is showing using an elevation model to get from point A to point B. What's the easiest way to get from point A to point B given the elevation, given the slope changes and the angles of the slope, stuff like that. We can calculate in the middle, on the bottom, a view shed. So, given a point location on a DEM, what are all the cells that are visible from that location? So think about a fire lookout. That would be a great example for this. Old fire lookouts from at least World War II forward were placed on the landscape on ridges and mountaintops, and they were trying to see as much of the land as possible. And here we might have a lookout tower, and those are all of the cells that are directly visible from that location, given the altitude above the Earth's surface of the tower. Down the lower right, buffers, so we can create kind of a distance away from it, but a very limited distance. So the distance grid up in the middle, upper middle example there is showing continuous distances across space at a given interval. So 30 meters, 60 meter, 90 meter, those types of things in each band. The buffer is you specify a particular distance, a specific distance away from the linear or point location on the Earth's surface, and it'll create just that. So we might say we need to have a 100 meter buffer around the roads, and we're not going to allow any kind of logging activity or something like that within that buffer. You can create that. You just say, ask the GIS to generate that, and they'll give you the cells back and say, here are the cells that are 100 meters away from roads. So this is where we can't have that kind of activity, or things like that. And the last one in the upper right is interpolation. So this is taking point location information and generating a raster from it. So a really good example for that you will actually do later in the class is to take point location from weather stations and then generate from those weather stations grids or rasters of precipitation and temperature across space. So we take the records from the point locations, in some cases in Idaho, for example, they're over 100 years old, over 100 years of information for these points. We can statistically create a surface, which is known as a statistical surface, of precipitation between those point locations where we don't have direct observations. So that's kind of a powerful thing we can do, combining vector and raster data in an operation. We take the point locations in the vector data set and create from it a raster data set. And that's something that happens quite often in a lot of different fields that involve work out on the landscape. Ecology, biology, geology, geomorphology, climatology. Anyway, so it is something that we will learn how to do in the class. And all these things are going to be things that you're going to get exposed to at some point during the class. So we've mentioned this concept before. We're going to get into it a little bit more detail here, and it's actually the topic of the next major lecture set of coordinate systems. And so every GIS data set that we have, if we're going to use it for anything, it really needs to be referenced to actual locations on the Earth's surface. And what we use to describe that relationship is a coordinate system. And so, as I've mentioned before, kind of think of it as an X and Y graph where we have an origin point. That origin point is linked to some location on the Earth's surface. And then all of the objects or rasters in the data set can then be referenced to that geographic location. That's what we call georeferencing. Sometimes we call it geocoding. On USGS topo maps, there are several different coordinate systems that get used routinely. And so they're a great example to pull out in class here. The different XY coordinate systems and their units that are shown on this map are latitude and longitude, shown in degrees, minutes, and seconds. The state plane coordinate system, which is measuring things in feet. And then universal transverse Mercator system, which measures locations in meters. So each of those systems is linked to geographic locations on the Earth's surface. The latitude and longitude system, or geographic coordinates, are linked to 0 degrees of latitude being the equator, 90 degrees being either North or South Pole, and then 0 degrees of longitude running through the Greenwich Observatory in England, and then measuring degrees east and west of that to about 180 degrees down the international date line. State plane coordinate system will be linked to some location in the state where it starts and has its origin point, and it's measuring distances from that location or that line or intersection in feet. Universal transverse Mercator is done similarly, although its origins are going to be the equator and then some line of longitude outside of the map area, but measuring distances and locations in meters from those origins. So anyway, if you learn how to use USGS maps, and there's actually another coordinate system used on them, the U.S. Public Land Survey System, which is totally different from these, and it measures areas, not locations. Anyway. So in GIS, we can display the same location point in different systems, UTM, geographic coordinate system, and state plane coordinates. We can see on the bottom of each of those inset images, it's a different coordinate. Okay. They're all describing the same location, but they all use different origin intersections for north, south, east, and west, and describing where those things are on the Earth's surface. In case of UTM, it's down to individual meters. With the geographic coordinate system, it's degrees, minutes, and seconds. A degree is approximately 69 miles. A minute is approximately 1.15 miles, or a nautical mile. And a second is about 104 feet. And then the state plane coordinate system, done in feet. So each of these has different levels of accuracy and precision. And they can all be used simultaneously to describe the same point location. And there are thousands of coordinate systems out there that we can use in our GIS analysis. Typically, you'll be exposed to, 5 to 10 maybe in most projects, pulling information together from different sources. And those different sources may have different standards and different coordinate systems that they require their workers to use. So USGS might require one system, a private corporation might require another. An individual researcher at a university may have a preference for another one. And you can combine all of those pieces of information, all those data sets, as long as you match the projections. So these are, that's something we'll get into in the next lecture set. I won't go into a whole lot more detail than that. But we can mix and match these things and get them to work together with a fairly simple operation. So two main types of coordinate systems that we have in our GIS work are unprojected or geographic coordinates and projected coordinates. In general, the unprojected coordinates are going to be basically the globe. Think of that whenever you see unprojected data, or if it's called geographic data, a geographic data set. It means it's describing locations in degrees, minutes, and seconds spherically on the 3D planetary surface. Projected data is if we take information, and the most common way of describing this is what's shown in the picture down there on the lower right. Put a light bulb inside a glass globe, and that glass globe has etched upon it the grid of latitude and longitude lines, maybe the shapes of continents, and then project the light through that glass ball onto a flat surface and trace the outlines. And you're projecting latitude and longitude coordinates, at least for the grid, maybe for the continental outlines, onto that two-dimensional surface. So unprojected means as it is on the globe. Projected means that we're changing it in some way. We're going to change the geometry a little bit in one way or another to display it in 2 dimensions. So we're taking the 3-dimensional reality and converting it into a 2-dimensional representation. In order for vector data to work properly, one of the properties that we have to investigate and understand is topology, or relationships between objects. And so, for example, here using polygons or lines, in order for a linear network of streets to work properly on the map, then we're going to have these point locations, the street origin or street end, the intersections represented by things that we call nodes, basically points, and the lines that describe the roads. And those relationships need to be as accurate as possible to describe the road network well. Same thing would apply to a stream network, where you want to have the headwaters, zones of the streams described well, the confluence of each set of streams as it moves downhill towards a lake or an ocean, or an interior water collection area, an ephemeral lake that appears sometimes and disappears during the dry season. Those spatial relationships have to be maintained in order for our vector data to be doing a good job of describing the Earth's surface. If we draw polygons and we don't do a good job of drawing the polygons, we can wind up with, as we see in the lower right, overlaps, gaps, basically slivers of things that don't really exist. And we need to avoid those by creating the maps properly in the first place, by digitizing them properly off of satellite images, air photos, or pre-existing maps. Okay, so some of these things, if the topology doesn't work, a lot of times it's because the human that was creating the data set made errors and introduced errors so that the geometry doesn't match. We need to have the geometry match to itself and to, as much as possible, the things that it's trying to represent on the Earth's surface. So how well our vector data matches the Earth's surface is commonly known as logical consistency. Does it match or not? And as we've seen on the last slide, we can create overlaps and gaps in polygons with linear features, undershoots, overshoots, known as dangles, making an intersection not happen by digitizing things wrong, introducing more things. Like here, we've got a line with a pseudo node on it, meaning it was a point location that actually doesn't need to be there in order to describe that linear feature properly. We could get rid of that node and have just the ends, and our line would be just fine. Um, or on the far right, introducing a loop by someone not closing things properly or not tracing things properly. In the digitizing process, we use a mouse to and drag it across the Earth's surface on our map. And if you twitch, you can introduce an error. So we try to avoid those. We try to be as logically consistent between what's actually on the Earth's surface, the features on the Earth's surface, and the features that we create in the vector data to describe those phenomena. Here's a great example of where things can go wrong. If we have different data sets and they don't match, then the analysis that we do using those data sets is going to be flawed, and it's going to be ripe with errors, and it's something that actually we have to face as a potential legal problem, because GIS work quite often is being used to support a decision-making process. So very quickly, the work that we do gets legal. Any information that we generate as a GIS technician or analyst will get used by someone making a decision. That decision can be challenged in court, and one of the ways that you can challenge actions by corporations, individuals, or government agencies is if they're acting on flawed information. And you can force them to go to court. In court, you can then be called as a witness. Your work can be called to question. You want to make sure that it's done as accurately as possible, using the best methods possible, using the best data possible, so that you don't run into problems in the legal arena. So take this, for example here, if we're doing some kind of work on the border area between South Dakota and Nebraska, which includes different counties in both states and Native Reservation, Pine Ridge Indian Reservation. And so if we just simply display our data sets and we see this amount of error in them, the first thing that you should think is, I need better information. I don't have anything, this is probably not something that you can easily fix if they're this far off. You're probably dealing with flawed information that was generated incorrectly by someone else, and you should probably find something, find a more recent and better done source of information to use in your analysis. Sometimes we can fix these things. For example, if they were using the same map projection, but the map projections were using different datums, if we reproject from one datum to the other, that might fix the problem. But that's a topic for the next major lecture on coordinate systems. But anyway, what we want is we want our data to match up as much as possible. We want the topology between different data sets to match as much as possible, as much as humanly possible, so that it's better information for making decisions, and it's something that's more defensible in court. So again, when we're working with or creating vector data, it's nice and much preferred to make sure that whatever you have in your data model mimics the real world as much as possible. So if two streets do cross, the lines that describe those streets should meet at an intersection, and that should be represented by the proper vector element in the data model. If an overpass crosses a street, the lines should not be intersecting. They should not be topologically linked, because they aren't. One's an overpass, one's an underpass. Those two roads don't physically meet each other. Two adjacent states should have a single identical boundary between them. So things like that. I mean, things that we take for granted when we look at maps. When we're dealing with the digital format, we have to make sure that the data is matching our reality as much as possible. And sometimes that means you may need to make corrections to them. Sometimes it means you may need to create your own data sets that are depicting those pieces of information, or do a lot of digging and find authoritative data sets that are done very well, that are topologically correct and do model the reality very well.